In this physics doodling video, we will explore the solutions of Maxwell equations and let the complexities of mathematics be handled by Wolfram Alpha, which is a free online web application. I'm hoping that you can also doodle along with me and go beyond what is in this video. Ideally, it is meant for the advanced undergraduate students or graduate students of physics and engineering. However, a curious person with high school education can also enjoy working with Maxwell equations. In this first part of the video, we will touch on the simplest wave solution, a bit complex wave, and a general wave. Let's begin. We have divided into following sections so you can use the YouTube features to directly jump to the sections. In Windows, you can use Control and forward arrow or backward arrow to jump to the sections. The YouTube call it as chapters, so we have written as chapters, but it is really section in our context. In Apple, you can use Option and forward arrow or backward arrow to jump to the sections. If you are watching on mobile or touch screens, you can use double tap with two fingers on the right or on the left to jump to the sections. Let's now go to the next chapter. Maxwell equations is all there is to explain macroscopic phenomenon related to electricity, magnetism, and optics. Here we have written down the Maxwell equations that is far away from free charges or electric current. We like to see if any stable electric or magnetic field can exist without the charges and currents. In this video, I will not go into detail of Maxwell equation, but briefly explain the equations. The first two are more like basic checks, which make sure that electric or magnetic field lines never disappear. It may bend and change direction, but never disappear. The mathematics is divergence of electric field and magnetic field is zero respectively. div is written for divergence. The third and fourth equation involving the curl, which essentially signifies the loop of induced electric or magnetic field around the change of magnetic and electric field respectively. The third equation is the famous Faraday law. The fourth equation states that change in electric field effectively behaves like current is called displacement current, which was theoretically discovered by Maxwell himself. The expression div is called divergence, and the curl has fairly complex mathematical representation, but we will let Wolfram Alpha handle the math. We now propose a simple wave equation, and we will do hands-on to see if they satisfy the Maxwell equation. You can learn from this hands-on experience and do it with many other combinations. We write the electric field in vector space notation. As you can see, each component separated by comma. It shows that the electric field is simply sine wave existing only in x direction. The magnetic field is in purely y direction. In the next slide, we will write Wolfram Alpha commands for Maxwell equation with the proposed solution. In this slide, we rewrite the Maxwell equation from the previous slide. We rewrite the proposed simple wave solutions that needs to be tested and the Wolfram Alpha commands. We will write the Wolfram Alpha commands throughout the slide with purple color. Here, one important thing to note is the space between two variables is interpreted as multiplication. One can of course write with star also, but we will prefer to write with space as it looks more elegant. These Wolfram Alpha commands are also provided in the description so that you can cut and paste for hands-on practice. We will briefly tell you how to enter Wolfram Alpha commands. It is very simple. We go to website wolframalpha.com and type the commands in this space and click on equals icon. That is all. Let's try and see. In this slide, we show how to enter the first Maxwell equation with the solution proposed. We will write the divergence of electric field. We need to see how the Wolfram Alpha interpreted the command, and we see that it is correct, and we see the result as 0. That is exactly what we expect. Divergence of E equals to 0. We do the same for second Maxwell equations and get the same result. The divergence of B is 0. So far great. Now let us go to the third and fourth equation, which is really the tough ones. When we enter the third Maxwell equation with the proposed electric and magnetic field, we see that it has interpreted correctly, but in the result, it did not quite do the cancellation. Still, Wolfram Alpha has put in a simple state that we can cancel it ourselves. Additionally, it gave the condition that the solution is valid, provided that k equals to omega divided by c, which is quite right for the wave equation. So we are really excited that the solution obeys the Maxwell equations and Wolfram Alpha was able to do it. The final fourth Maxwell equation is also very similar to the previous slide. In the results, however, we need to perform simple cancellation. It also suggests that the same condition k is equal to omega divided by c needs to be satisfied so that the equation remains valid. So finally, we have proved that simple proposed solution obeys Maxwell equations, which means that electromagnetic wave with simple sine wave solution with electric field in x direction and magnetic field in y direction can exist. This is quite an achievement that without doing much math, we are able to prove it. Encouraged by this, we now dare to try with more complex electric and magnetic field and see if it also satisfies Maxwell equation. Let's do that in the next slide. At this point, you must be excited because you could prove a simple wave that can exist without the need of charge or current. You also must be excited that without doing the elaborate math, you could prove it. Now let us increase the complexity of the proposed solution by multiplying a cos cube term as shown in red and see if it satisfies the Maxwell equations. We can use the same Wolfram alpha to see the plot of the sine cos cube term. It seems like a distorted wave, still it has a periodicity. Before we start solving for the complex wave solution, let us simplify a bit. From the last example, we have seen the condition omega is equal to c times k. Why not substitute here so that the Wolfram alpha has to do less work to solve? Let's go to the next slide. Following are the proposed complex wave solution and the Wolfram alpha commands. In this video, we will do it only for the last two curl equations as it gives interesting result. As mentioned before, we have put all these Wolfram commands in the video description so that you can cut and paste and do it for all the equations. This is for the third equation. It interprets correctly and gives true. That is a bit amazing that Wolfram Alpha was able to do it all the way to the end. The next fourth equation is not so easy for Wolfram Alpha. Let's see. By having 1 by c square, the Wolfram Alpha is not able to simplify completely, but we will cancel things ourselves and see that right hand side is same as left hand side. At this point, we are again excited, but at the same time suspicious that a complex wave is also a solution. So what about a general wave solution? Before we venture on a general wave function, let us understand as to what is a wave. Nothing profound. Let us see some visuals and figure out a general function of the wave. Let's take the first case. Is this a wave? I'm sure everyone will enthusiastically agree. We have been writing this function since high school, which is sine of kx minus omega t. Let us take the second complex case. This we have just done, and we have written the wave function as this. Let us take the third case, which is a pulse. You may have some initial doubt, but if I were to tell you that this is just like simple sine wave, but the amplitude gets diminished to almost zero, except in the small space, which is also moving with time, you may agree that this is a wave. What about fourth case, which is actually a white noise? It has no period or wavelength, but if you see carefully, it has a random beginning, but once created, the pattern remains frozen and moves with time. This is exactly the same as in all the previous cases. The created pattern remains frozen in time and moves with velocity of wave. So this must be a wave too, and can be given by this general function f of z minus vt. It is aperiodic wave, which means it does not have period or wavelength, but it still classifies as a wave. If the wave is periodic, of course, then we have extra constraint, which is v equals to omega divided by k. Now that we have established a general wave function, let us modify our previous electric and magnetic field to a general wave. Note that we still have electric field in x direction and magnetic field in y direction. Let us write the Wolfram Alpha commands and see how it is interpreted. Let's plug in the commands related to divergence, and as expected, the Wolfram Alpha gives the result as 0. That was easy. Now let's plug in the curl equations in the Wolfram Alpha and keep our fingers crossed. To our surprise, the result shows that the Maxwell equation is indeed satisfied provided v equals to c, and secondly, the derivative of wave function exists. This indirectly means that the wave function should not be discontinuous. In fact, nature is clever in telling that the charge source that is producing the wave function does not disappear or randomly appear somewhere else. This is principle of locality. I think it is quite amazing that a simple general function has so much to teach us and obeys the Maxwell equation. By the way, f dash is derivative of the function with respect to x minus vt, which is quite clever from Wolfram Alpha. If you have reached up to this point in this video, I presume you are interested in seeing more such videos. You can search for me in YouTube by these keywords or directly go to the URL mentioned. You go to the playlist Physics Doodle to find more such videos. By the way, my name is Mahesh Yadav. I have PhD in physics from Rutgers University, which is the State University of New Jersey in USA. I'm about 60 plus years old, nearly retired, and therefore no worries of exams, career path, or family obligations. That makes a big difference in thinking physics with a clear mind. This is all for my introduction. Let us now go to the next chapter. Before we create a final picture, let us see some other features that can be easily concluded. First is electric field is C times B. Secondly, E is always perpendicular to B. And the last is the electric field is oriented with respect to magnetic field in such a way that it provides clue to the direction of wave. Mathematically speaking, cross product of vector E and B is in direction of the wave. We can use any of the example mentioned in this video to prove it. Let us use general wave function that we have been dealing with in the previous slide. We see that the strength of E is C times B. Let us say they are proportionate. The bigger is the electric field, the bigger is the magnetic field. Next we see that electric field E is in x direction and magnetic field B is in y direction. We like to conclude that E is always perpendicular to B. You may be thinking that one example is inadequate to confidently say that electric field is always perpendicular to magnetic field. You are right. However, I will say that you can try to have other wave function and see for yourself with Wolfram Alpha if you can satisfy the Maxwell equations and prove otherwise. Mathematically, E is perpendicular to B would mean the dot product between two vectors E and B is 0. This can be easily tested by following Wolfram Alpha command. You just need to put the English letter period as shown. For the cross product, we can also easily see the following Wolfram Alpha command. Here we have English letter X. You can do it yourself and see that you will have a positive value in z-axis, which means the wave is moving in positive z direction. Glad we have finished all there is to develop the character of the electromagnetic wave. Let's go to the next slide. Now let us bring all the things together. Let us pretend that we have not seen the three waves plotted in the left, and let us build piece by piece the core idea that needs to be satisfied to make electromagnetic wave. We will continue to have electric field in x direction and magnetic field in y direction and the wave traveling in z direction. Let us start by drawing some electric field in x direction, which will be part of the electromagnetic wave. It is shown as red vectors. Our first rule is to have magnetic field perpendicular to electric field. So we draw a magnetic field shown in green. Our next rule is to have E cross B in the direction of wave propagation, which is in z direction. We see that three of the magnetic fields are not correct. So we correct the direction of the magnetic field. Now, in all the cases, E cross B is in Z direction. Now let us go for the third rule, which is magnitude of electric field is proportionate to magnitude of magnetic field. The longer is the E, the longer is the B. If E is short, B at that point is also short. We see that in our figure, the magnetic field are not proportionate, so we'll make them proportionate. And now they look proportionate. Let us make the fourth rule, which is wave function must not be discontinuous. To understand the rule, we need to know the neighboring electric and magnetic field. The rule can roughly be translated as if a person living in the house is tall, his neighbor should in general be tall, maybe a bit shorter, maybe a bit taller, or at the same height, but never very short. That will mean discontinuity. Very similarly, of course, a short person will in general have a short neighbor. Let us draw that, and I hope that this diagram conveys the idea of the function not changing suddenly. We can see that in one case, the electric field is very small and it has no neighbor, or electric field is zero. That is quite possible too, and it does not violate the rule that the function is discontinuous. That are all the rules there is for electromagnetic wave to exist in vacuum, which are far from the charges and current. A piece of wave has absolutely no relation to another piece of the wave. It could be part of the same wave or belonging to a different wave. The wave is created from the behavior of the source. If the source is simple and periodic, the wave is also simple and periodic. If the source has a random or complex acceleration, the wave will behave the same. Before I end the video, I will tell you one more math trick relating to the wave. Imagine you take this wave snapshot like a photograph at time t equals to 0. Now it is a function of position only. It is a static function like the picture on the left. Now remove the condition of time t equals to 0 and you get the same static frozen piece but moving. This is how the wave behaves. I hope you have learned a lot of interesting things in this video and a lot of things to work out. That is all. Bye bye.